Let's consider the following problem. Consider a uniformly charged non-conducting sphere of total charge q and radius r. Find an expression for the magnitude of electric field as a function of r for a, r greater than r, and b, r less than capital R. How would these answers change if the field was conducting? Alright, so we're just going to basically look at this question very carefully by first drawing a picture. This is an exercise in Gauss's law, and the important thing to keep in mind when doing Gauss's law is to draw a very clear picture of what you're after, right? So let's draw a uniformly charged non-conducting sphere. So let's draw a sphere. Okay, and let's basically denote that this is a sphere by drawing front side and the back side. Okay, beautiful. So that's my sphere, and this has a radius of capital R. And there are 2 points which I care about. First of all, I will care about a point here. All right, let's say this is P, which has some radius R greater than R. And then perhaps another point in here. I'll call this not Q, maybe P2, which is some radius R less than R. Okay. All right, so we'll basically work on this in 2 parts. All right. So the key idea for Gauss's law is that the electric flux, which is denoted by capital phi, is equal to the electric field, dot that with the area, right? Is equal to the total charge inside divided by epsilon naught. And for those of you who recall, basically the relation between epsilon and k, which is Coulomb's constant, k is equal to 1 over 4 pi epsilon naught. All right. So we're going to use this very simple equation here to basically get at this problem, right? Now let's consider the first case, r greater than r, right? So case A, right? So to basically look at this problem, let's write down that the electric field dot this with A is equal to the charge inside, okay, over epsilon naught. Okay, now the key idea is that for r greater than r, right, let's draw the imaginary spherical shell around this thing here, okay. For r greater than r, the charge that's contained inside is really just all the charge that's contained inside, which in this case is charge q, right? So in this case, q inside is equal to q, right? Now this by itself tells you what the flux has to be, all right? This is not really just E times A, it's really the integral of the electric field times basically the area. And in fact, these should be vectors in front of everything, all right? Now, we should be careful because the only reason why Gauss's law works in this case is that this sphere is spherically symmetric. That is, if I look at this problem in many different ways, if I keep turning it, rotating this thing all around, I get the same problem over and over again, basically, right? This electric field here would be the same configuration as this problem here, would be the same configuration as this problem here, right? So by basically knowing that the electric field has to be spherically symmetric, this allows me to actually solve this problem, right? So let's go ahead and do it then, right? So I know E is basically more or less the same direction everywhere. It's pointing outward, right? Okay, so we do this. This becomes simply the electric field, right, times 4 pi r squared is equal to Q inside is Q over epsilon naught, right? And so this just becomes E is equal to Q divided by 4 pi epsilon naught r squared, and you're done in the r hat direction, right? Now, there's one thing you just be very careful about, okay? Or you could be simplified more. You know that this thing is really K. You could write this as basically K Q over r squared r hat, right? And then you're done. Now let's try part B, okay? right? So for B, right, R is less than equal to capital R. Right? So for this example, you can use the same thing again. The flux is equal to E dot A is equal to basically Q inside over epsilon naught. Right? Now, in this case, Q inside is not Q, right? So let's draw a little sphere in here, right? It's only part of it, okay? It's not the entire charge, right? So in fact, Q inside is equal to the integral of the charge per unit volume, rho, times the volume, okay? But it's uniformly charged, right, as I stated earlier in this problem. And so this integral is just basically rho times the volume as a function of r for r less than equal to capital R. Right? So what's volume of a sphere? Well, volume of a sphere is pretty easy. That's just going to be equal to rho 4/3 pi r cubed. Okay. And the charge per unit volume, really, this is going to be equal to Q divided by the volume of the entire sphere, right? Times 4 pi over 3 r cubed. Okay, and the volume of the entire third is just 4/3 pi capital R cubed, right? So if you combine this together, that means that Q inside is equal to capital Q. The 4 pi over 3 cancel each other out. R over R cubed. Okay. All right. So let's take this, plug it in here then. All right. So what I have here is basically E vector, well, the magnitude E now, 4 pi r squared, the area of the sphere, is equal to Q inside is just basically Q r cubed over capital R cubed divided by epsilon naught. Okay, and then simplifying everything quickly, we will get, let me just see if I can write this thing here. This is going to be equal to, implies the electric field is going to be equal to Q over 4 pi epsilon naught r over r cubed, because the r squares will cancel one factor of the r cubed there in the r hat direction. All right, and so therefore you're done. Now, how would this answer change if the sphere was conducting? So what is the difference between a conducting sphere and a non-conducting sphere? Well, a conducting sphere basically has the charge rather than spread out evenly. It's all on the surface, right? So in fact, part A would still be true, right? It is still the charge that's contained inside this large shell. But part B would not be true, right? In fact, inside of R less than, right? For conducting, let me try this. For conducting, for R less than R, there is no charge. Q inside is equal to 0. So in fact, what happens is that for part B, in this case, all right, so for part B, this implies the electric field inside conducting sphere is 0, right? And so there you have it, the basic example of this very simple problem, which illustrates a lot of different things and a lot of different properties of Gauss's law. Hope this was helpful.